My name is Sven Diyar Kuhi and I'm Simulation Product Manager at Intercad. Today webinar we will talking about SolidWorks Simulation Premium Dynamic Test and specifically going to earthquake simulation. Alright, so if we look at the objectives of presentation today, we have a very quick recap about the definition of static and dynamic analysis and what sort of equation we are solving in the software. Then we are going to have the main focus on dynamic analysis definition, type, and its capabilities. Well, we're talking about loads and dynamic loads, different type of loads we have, and each load might end up with what sort of dynamic analysis. Specifically for earthquake analysis, we performing one type of linear dynamic analysis which we called response spectrum analysis. We're going over its definition and the procedure of how we make it. We complete our definition cases by representing a real case study as response spectrum analysis on electronic, and the other one which is earthquake analysis on a building. All right, so let's have a look about the SolidWorks simulation package. It's available. You can have the simulation as a simulation standard package, where you are able to do linear static analysis, motion-based analysis, and fatigue trend tracker. You adding the capabilities and range of the application by upgrading to SolidWorks Simulation Professional. Well, you can see frequency, thermal analysis, drop test, and bucklings, and the other things are simply adding here. And the main focus which we are going to use the capabilities is SolidWorks Simulation Premium, and specifically we're talking about linear dynamic studies. So the presentation today, earthquake analysis, is considering linear dynamic analysis, and it is within SolidWorks Simulation Premium package. All right, now first, we are going to have a definition about static analysis. So in any static analysis, as you know, we assuming the loads are constant and applied very slowly until they reach their full values. Therefore, we can assume that velocity and acceleration fields are nearly zero. So if we are simply considering a single degree of freedom system as mass and spring, by applying a force, we get a displacement of U depends on mass and K of the system. Well, basically we are solving F equal to KU, and K is stiffness, U is displacement or unknown, and F is the load vector which is known. When it's coming to the dynamic analysis, we are talking about impact forces which is varying with the time. So we have a force time dependent. It could be very quick, it could be slower, but one thing for sure, in such a this analysis, velocity and acceleration fields are not zero anymore. We incorporate in frequencies, impact, and dampening in dynamic systems. Well, the above equation is now getting modified to consider MA, so U double dot T means displacement second derivative times mass, which is MA, C, which is dampening, one of the most important, let's say, factors in any dynamic testing, times velocity, and K, which is the stiffness times displacement, adding all these terms equal to the force time dependent. Well, if you look at the figure, we have the same system, we have a dampener, we have K, and we have force and displacement varying with the time. So in any dynamic analysis, force is time dependent, therefore displacements are time dependent as well. Now from this point, we can have a second split. Well, we are considering if the K value or C values are time dependent or not. Now let's move to the next slide, and this is exactly where we are, let's say, defining different type of dynamic studies as linear dynamic studies and non-linear dynamic studies. But one thing prior than that is when we, let's say, exactly applying a dynamic analysis. The main rule is if the frequency of a load is larger than 1/3 of the lowest or fundamental frequency of a system, a dynamic study needs to be applied. In linear dynamic studies, loads are time dependent, but mass and stiffness and dampening matrix do not vary with the time. Therefore, such these studies are based on frequency studies, and simply as the first or lower modes of vibration contribute more significantly to the response of the structure. In such a study, calculations are based on the response of the model by accumulating the contribution of each mode to the loading environment. And also one very important fact, we're talking about linear, and this linearity is considering the material. So if we have a nonlinear material and a dynamic loading, there is no other option to move to nonlinear dynamic studies. We'll be calculating the displacement fields as unknown, primary unknown of the field, at every time step with the given or applied load. What we are getting is nonlinear stress, strain, velocity, and acceleration from such a study. All right. Now, up to this point, we have simply mentioned or repeated that in any dynamic studies, we are talking about time-dependent loading. Let's have a closer look to the dynamic loads. We simply, let's say, categorize them in deterministic loads, where the loads are well defined as a function of time, and we can predict their behavior or changing fluctuations or changing precisely. They can be harmonic, periodic, or non-periodic. Well, with having such a disloading and performing a dynamic analysis, we're getting a very deterministic result as well, means absolute and precise result. Well, in some cases, we can't explicitly define our loading as a function of time. These are non-deterministic loads. They are mostly described by statistical parameters, and we are getting an average or non-deterministic result over them. Well, if you look at the figure here, we can see different type of loads. For instance, if we do have a periodic loading, then we are able to do a modal time history analysis. If we have harmonic loading, yeah, definitely we can do a harmonic analysis, linear dynamic. And also, if we do have general loading as no prediction on the magnitudes and fluctuations, we can do random vibration analysis. And one thing in particular, which is considering today's webinar, is a shock loading. Well, the peak response of the structure to this loading is very important for us. That's why we're taking a response spectrum analysis, and that is well documented that such a analysis are pretty quick and beneficial to do an earthquake analysis in our system. Okay, now let's have a closer look to the response spectrum analysis here. Earthquake analysis can be performed by response spectrum analysis or RS analysis, which is a linear dynamics, let's say, statistical analysis method. Well, you can see in the picture as you have a base excitation and you would like to measure the contribution from each natural mode of vibration and to see the structural seismic response on such a space excitation. This study definitely can provide us an insight to dynamic behavior by measuring pseudo-structural acceleration, velocity, displacement as a function of, let's say, time, or otherwise we can say as a function of frequency at some certain level of dampening. All right, now let's look at the procedure. What we need in any response spectrum analysis is input as a response spectrum curve. Such this curve is the peak response of the structure for the range of let's say, basic excitation or time varying load and measuring the peak response of the structure. For instance, if we look at the picture here, we have multiple, let's say, single degree of freedom, and all of them are subjected to the base acceleration excitation, as you can see here. Each structure has its stiffness and mass. What we do is simply, since we have the mass as a known, stiffness as a known, then definitely we can calculate the natural frequency of the system. That is x-axis of our response spectra graph. Then under such a dish loading with the known values of m and k, we're measuring the response, and that is the y-axis. So if you have the response spectra graph, means the peak response of the structure to a dynamic loading, then in response spectrum analysis, we entering such a disk curve into the analysis and simply combining the effect of these peaks with the different sort of methods and look at the maximum response of a structure while such as this loading is going to be applied to the structure. Okay, such a these let's say graphs usually are coming from a testing. So either we have an accelerometer and located in let's say our system, recording the acceleration by time and using the Fourier function to convert it to acceleration and frequency, or either the response could be plotted as a maximum displacement versus frequency, or velocity versus frequency, or let's say acceleration versus frequency. But one thing for sure, the entry of response spectrum analysis, which is a graph, is coming from a test data. This is a physical test data, and in a different frequencies, we're getting the response of the actual component. So if we have these single points and we would like to simply add them together and see what are the responses of the structure to that, we need to go to the second step. Well, we are combining the modes of vibration. So therefore, the maximum structural response is calculated by summing the contribution from each mode. We have different methods for combination in SolidWorks available. The first one is square root of sum of squares, SRSS. Well, simply estimated the peak response by the square root of the sum of the maximum model response squared. We have different schemes, such as absolute sum, complete quadratic combination, and also Naval Research Laboratory. More information if you like to receive, we can definitely provide on this one, and we are not going to waste a lot of time on these, let's say, example, let's say, details of each mode. But one thing for sure, what we understood up to here is we have a system, and system has its dampening ratio, stiffness, and mass. The peak response of the structure to a base excitation is what we are going to apply and measure, and then for a different mode of frequency, those peaks needs to be added together and get the new response. That is required response spectrum analysis here. All right, now it's a good time to move on our first case study. The first case study is talking about an electronic unit inside a projectile. Well, the projectile is dropping down and it's undergoing to a shock load. What we have in a real test, we have an accelerometer located on the electronic mounting location, and it's recording the transient acceleration data. When we get acceleration with corresponding to the time, we need to transform it to the figure as you can see here. Acceleration described in the G and frequency in Hertz. So you can see the experimental data is being recorded and transformed, Now in the software, in the first case study, we are going to represent that curve with two step lines linear. So we're estimating the first section as 1 to 2 here, and this is the first step of acceleration versus let's say frequency, and we simply estimated the second section of the curve by 0.1 and 0.2 as a linear line. So that might be close enough as a, let's say, curve fitting to the experimental data, but definitely you can enter the rest of the data if there is any significant, let's say, variation on frequency and acceleration. What is required? First of all, before doing any RS analysis, we have to perform a frequency analysis to find first the list of resonant frequency and look at their mood and shapes, and then also look at the mass participation factor. It's more than important for the direction of collusion or predominant, let's say, direction of displacement. We have more than 80% of the mass of the system to contribute in vibration. In that case, we can guarantee that all important modes of vibration is being incorporated into our study and be getting the maximum response correctly calculated. Okay, so this would be our first case study, and in the next case study we're definitely going to have the same let's say sort of testing on a shell structure building, and simply we have a velocity field. As you can see, this is my response spectrograph. Again, there is an accelerometer or a velocity meter that is being located into the building or recorded the earthquake sort of seismic behavior, and it's being converted to the velocity versus frequency. And this shell building is being fixed, means it's been located on the ground, and we would like to see how it is displacing, what is the maximum response, what is the stress distribution, and also looking at the prob, average value, and other stuff. Okay, now it's a good time to move to our case studies. All right, let me bring the first case, and here it is. So as we can see in the case, we have an electronic device. Well, it should be located on a projectile like that, but we are not going to consider the projectile by itself. We can simply suppress them and then have a split face to make it fully fixed on the face. All right, now what we have to do is going to our study advisor and going to new study, name it as you would like, and the type would be linear dynamic. By selecting a linear dynamic study, you can see we have multiple options: modal time history, harmonic analysis, random vibration, and also we have response spectrum analysis, which is the main focus here. So it depends on the type of load, as I've introduced it in a couple of slides ago. We are going to select any of these options. So simply we get the response spectrum analysis as our study type. Clicking OK, and here is what we have. Like as you experienced it before, you have a list of the parts. All the materials needs to be assigned to each individual part. You either can go apply all material to all, select from your favorites, or go and select individual and simply access the SolidWorks material library. For those who are not really familiar with our web portal access, so by clicking here, you will get the web link to access our material web portal, and simply you are able to say, I would like to perform a dynamic study, and it is a linear elastic isotropic material. I would like to download fatigue, factor of safety, or thermal loadings data as well. It is talking about metals and also, for example, in steel category, and then simply locate your material. By do the locate, and then simply you access all available material here. You can simply review them or making more specific investigations by clicking on them. The pop-up window will bring all the material properties, and you simply can let's say look at the material model, raw data, and material name and other specification. If you're happy with what you got, you can download it and definitely add to your SolidWorks library. Okay, so the first step, which is material data, is being added. We used LOI on these components, as you can see here. We selected ceramic for these two resistors, copper for the microprocessor, and also the ceramic porcelain on the other chip as well. The board is being defined as a shell, and we have all bonded connection with all these components together. The first thing we have to do is to fix the back end where it's locating on the projectile. So edit definition, select the face, and simply say it's fixed. Now, the main thing in our dynamic study is your external loads, which could be a prescribed displacement, uniform base excitation, or selected base excitation. If you're looking to what I've applied, if I go edit definition, you can apply displacement, velocity, or acceleration in all three directions, X, Y, Z, to be a time dependent or a curve, or either linearly such a let's say acceleration to apply. But I'm not going to the details of what I've applied here. Just hold it for now, and I would like to do the next thing here. As we said, it is very important to understand the natural frequency of such a system and also the mass participation in the direction of collision. How we can do that? We need to perform a frequency analysis here. In order to do that is simply you're going to your study properties and defining how many natural frequencies you would like to capture with your study. So right now we put 75, and then simply if you look at your run study tab, you can see run frequencies here. By clicking on here, you simply running just the frequency analysis to simply list the natural frequencies of the system, its time, and also their mass participation. And also definitely you can plot the mood and shape of the natural frequencies. Okay. Now, since this is done, right click and you simply go to list resonant frequencies, and simply let me maximize it from mode 1 to mode 75. The calculation is done. What we have here is the frequency as radian per second, frequency in hertz, and also the period or the time this frequency or vibration happened. So you can see the first natural frequency is 18,157 hertz, and it is increasing to 1.979 E5 hertz. So that is the first 75 natural frequency of the system. So we have now an estimation about the frequency of vibration. The next important thing is right click and look at the mass participation. What is very important for us, since this electronic unit is dropping down in Y direction, we have to make sure we are capturing the correct frequency or important frequency through that, let's say, collision direction, which is definitely a Y direction. Therefore, all the components should participate in vibration. How we can check that is from mode number 1 to number 7, you can see there is a summation of mass participation. In X, 70%. In Y, is nearly 80%, and in Z is 79%. So what is very important, in that important direction, we need to at least have 80% of the mass participation, or by other means, we are capturing all the important natural frequencies of the system contributed in our vibration. So performing the frequency analysis showed us we are just need to consider 75 modes of vibration, and this is how we get a precise answer, as all the components are contributing to our vibration. Okay, now this is the time we have to bring again the loading of the system. If you remember, let me bring back our let's say test data, and you have a look. Here it is. As you can see here, we do have 0, 0. It's going through around 3,500, and the frequency according to this is around 5,000, and still remain the same. What we need to do is to simply say acceleration is going to vary with the frequency by that curve, the red curve. So reading the data correctly, get back to base excitation, edit definition. You can see I have applied acceleration in y direction output 1g, and then I've edited the curve. So 0, 0 is the first one. Second point was 5670 as hertz, and simply, sorry, let's put it back. And the let's say response was 3500, and then it's remained the same onto the frequencies of 11,000 and same acceleration. So simply we put the magnitude of acceleration to be frequency dependent as the entry of our base excitation. So the unit base multiply by these values at a different frequency. For the range between 0 and 5670, we got that much. For the range above this, we're getting the same. All right, but the variation is like what we can see here. A linear variation of the frequency of acceleration up to 0.5670, and the rest would be the same. That is a quite precise representation of what we have defined on the curve, as you can see here. So 0, 0, and then it's going to be here, a linear curve, and for the rest is a constant curve. Okay, so we've done this, and we are ready to go and run this study for a linear dynamic study spectrum analysis here. So solving the system, and we simply can review the result after the solution is being done. One important thing always, guys, when you performing any analysis, you have to check the mesh quality and make sure you've got enough elements, and your frequency or list of frequency or time or period or anything else is not changing with your mesh, and the mesh quality is okay. So you can see the max and minimum element size, mesh quality is high, and simply nothing is reporting wrong. And since the let's say the study is finished, now we can review the result in any spec we want. First, displacement. As you can see, we recorded the displacement happening on the edge of this circuit board. So this is where the maximum displacements are happening, and we can read the magnitude of the displacement, which is away from its fixture. Second, we have to look at the stress results. The stress results are simply showing us the maximum stress are happening on the pins. So whatever value you get, well, it can be, let's say, converted to megapascal, you can see it is 40 megapascal, and it's now the time if you are comparing those values with the yield strength of the material and see if there is any failure happening in your structure. And the last one, which is acceleration, is what is being made by myself. By right-click on the result, you can have a defined stress, displacement, velocity, and acceleration. So acceleration in any unit you like, and also you can have shown on the mesh. Look at this, and here is where we have the maximum acceleration recorded in our system. Alright, so with that one, and combining all the peak response from the response spectra, we found that the maximum stress, maximum displacement, and acceleration distribution through our components. Then last thing I would like to mention here, in your study properties, you can simply go and change the response spectrum combination method from what is being assigned right now, square root sum of the squares, to any other ones as you would like to select it. Okay, as we said, details about them and how they are applicable is something that we can provide you offline if you like, and refer you to the references, and this is not the main focus of our presentation today. Okay, so we have done the first case study. It's looked like a shock load to a structure using response spectrum analysis. Now let's move to the next case. Next case, we are considering a building. Well, it is subjected to, let's say, an earthquake. Well, you can see one good thing we have is the shell elements or shell or surface, let's say, CAD geometry can be simply used in our linear dynamic analysis. That could save you a lot of time for simply simplify your geometry with the shells rather than the solid elements, and a long time to resolve. All right, so if we have a look here in our dynamic study, what I've done, I simply get the list of my shells, make sure they are all connected with the bonded connection as a general. Thickness and material is simply being assigned to them. So if we go to edit definition, you can see 200 millimeter, and the offset is simply being mid-plane. That is all been defined, but again, if you are taking a surface, let's say CAD geometry, and it's going to be converted automatically, well, it is more than important when you're doing such a thing is making some, let's say, simplification to the model and make it meaningful to your FEA study, rather than to have, let's say, a very detailed sort of representation and spend a lot of time for unnecessary calculations. Okay. The rest is what I've done is my base excitation. So simply I've put a northwest, north-south means along the z-axis as 1 meter per second velocity. And the profile of this velocity variation as an earthquake entry, as you can see, is being here. Now, one easy thing to do is entering the value. If you have an Excel file, just copy and paste it here. Otherwise, you can get the curve if it's a SolidWorks curve natural file. You can see it has been addressed to read the curve from SolidWorks C drive program files, SolidWorks Corporation folder, and this address, as you can see. Well, I can go back here and show you the same address, and simply from my study folder I have this type of file, CWCUR, as a curve file, simply been copied and pasted to the folder which the software is getting the curve from. Okay, so simply I've put it here, and then I can get the curve. So the frequency curve is being shown here. But again, there is not necessary to do always like that. If you have an Excel file for your spectrum graph, simply copy and paste the values of X and Y. X is the curve data for frequency. Y is the response, which is maximum velocity values. So either if you are selecting acceleration, would be maximum acceleration values. Multiply by 1 is exactly the same as what we want as a curve here. All right. So I've done my loadings, I've done the components, and simply I have to fix those edges. The building is located on the ground, and then simply I have to run the analysis. But beforehand, as we said, it is necessary to go and run frequency analysis first. Now let me cancel this. One thing I have forgot to say is go back to our study properties and look how many natural frequency. Let's start with 10, and I'm clicking OK. Let's run the frequency analysis. So we're starting from low magnitude of frequency because more frequencies take more time to solve and simply affecting your linear dynamic analysis as well. So by doing that and going to results, if we look at the list mass participation, you can see in Z direction we got 90%, in Y direction we got 58, and in X direction we got 85. Well, as we said, our base excitation unit is simply applied in Z direction, and you can see the arrow here. Therefore, since we got 90% of mass contribution or mass participation, then we are happy to take the result to the next level. We enter our curve, we fix the structure, material has been assigned. Now it is time to run this study by contributing the peak response of each individual frequencies, combining together with the method SSRS, and simply get the structure response as you can see here. So as we expecting, we have high stress values around the fixtures. On each story we can simply go and prop, stress, displacement, and simply look at the prop and go here on the face, look at the sum, average, mean, and max. That is also available on selected entities such as line, update, and look at the variation over the time, over the distance, sorry. So it's up to you to make at location means one single spot, on selected entities such as a face, update, look at the average value if it is required, or if the location is look like an edge, then simply look at the trend by its distance. So it can give you a very good estimation about the response of the structure to a dynamic loading such as earthquake entry. All right, so what is very important to understand, we are getting mostly positive value when we do the response spectrum analysis, and as we said, this is a statistical method of combining the peak response of the structure in a different frequency when we enter the graph spectra. That is again very good estimation when we have huge models such as a building. Well, it might take a very long time to resolve with the nonlinear dynamic. But again, I'm emphasizing more precise answer requires a lot of time to study. Well, you're creating a nonlinear dynamic study. You have the time varying load, and simply with the very tiny steps, you have to solve the model. But in so many cases it's not practical, and it is always recommended to look at such these complex, let's say, structures to be run with the response spectrum analysis as a statistical linear dynamic method. Okay guys, so that is wrap up our webinar today. What I would like to bring back is simply a review of what we have achieved. We've done 2 case studies. One is drop test and second was an earthquake test on a building. If you need more information technical, please contact me, svandyar.kuhi@intercat.com.au. But if you like to have a more commercial discussion, you have to contact John Belsham at john.belsham@intercat.com.au. Alrighty guys, I would like to thank everybody for participation and hope to see you soon in the future webinars.